I don't know. Well, you can just go back, watch the YouTube video, copy it over. Thevenin's and Norton's Theorems, lecture 1.4. There are ways to simplify our models of circuits. So, how many of you have seen Thevenin and Norton's theorems before? Okay, so a few of you have.
About this week.
Okay.
Wait, last week. It was last week.
Okay. Homework, yeah. So I mean, some of you have read in the textbook, but yeah, it's really not too bad. The textbook does a pretty good job, I think, of explaining it, but I hope to do a better job or a different job. We don't have to compare. It's not really good to compare. Okay. So the idea is that we can take a complex circuit and come up with a simple representation for it. So Thevenin's theorem, it's pretty remarkable actually, states that given a linear network of voltage sources, current sources, and resistors, the behavior at the network's output terminals can be reproduced exactly by a single voltage source VE in series with a resistor RE. Well, that's pretty cool. So you could have thousands of resistors and sources, and you can simplify down the same exact behavior can be reproduced at its output terminals by a voltage source and a series resistor.
And give us a question, why do you need 1,000 resistors?
You might need 1,000 resistors. I don't know. It's hard to say why you would need it. I don't know why, but you might. Let's say that you did. Or the other way that this is used is if there's a black box and you don't know what's in it. You can come up with a model for it just based on this theorem. So the only thing that really needs to be specified are the two quantities. What's the equivalent voltage, VE, voltage source, and what is the equivalent resistance, RE? So that's where the work is. Like the theorem is like done for you, so you don't have to do that. But now you just need to decide what VE and RE are. So when you come up with a Thevenin equivalent circuit, all the work is just determining VE and RE. So RE is easier. So the equivalent resistance, RE, of a circuit is the resistance between the output terminals with all inputs set to 0. I mean, that's really all I need to say, but I will elaborate on that. Setting a voltage source to 0 means the voltage on both its terminals are equal, which is equivalent to treating it as a short or wire, right? So if you have a voltage source, you say, oh, okay, so if it was a 5-volt voltage source, the difference between the two terminals would be 5 volts. But if you're setting it equal to 0, the difference between the input and output, or the difference between the two terminals is 0, right? Which is the same as a wire, which has a voltage difference of 0. So you could think about just putting a wire in the diagram wherever a voltage source shows up when you're trying to find the equivalent resistance. Now, if it's a current source, then it means that there's no current flowing through that element in the circuit, which is equivalent to having an open circuit, right? Or disconnecting, having no wire there at all, so no elements. So that's how you zero out a current source. And then all there is left are there are a bunch of resistors, right? And you have to determine what the resistance is between two terminals. That's just going to be a bunch of series and parallel resistor equivalences, right? Which we know how to do. It's what we're like really comfortable with circuits, right? Like from physics, like I've noticed the knee-jerk reaction when you blank out on an exam is just start combining resistors. It's cool. I mean, I get it. Everybody blanks out and just starts doing their default thing. Occasionally, it's just, just the nature of whatever we are, I guess, humans. So that's the equivalent resistance. It's pretty straightforward. It's really not that hard to find. The equivalent voltage can be harder. You have to do some circuit analysis. You have to decide what the voltage is at those output terminals. Okay. So the equivalent voltage source, VE, is the voltage at the output terminals of the circuit when they're left open. In other words, disconnected from a load. So you don't connect anything up to the output terminals. You just find out what the voltage would be if you didn't connect it to anything. So it typically requires some circuit analysis with Ohm's and Kirchhoff's laws, which we can do. We can write down those equations and try to solve for stuff. We don't know how to do it systematically yet, but we're going to get there. But unsystematically, we are good at that. Okay. Now Norton's theorem, we're going to do an example with both. So just, I know that you're worried that I was just going to keep moving and not do an example, but I am going to. But we're going to do Norton's theorem first before we do the example. And it's very similar. It's sort of the dual to this, to Thevenin's theorem. So given a linear network of voltage sources, current sources, and resistors, the behavior at the network's output terminals can be reproduced exactly by, so far, exactly the same theorem, right? Now this is the part that's different. By a single current source, i.e., instead of a voltage source, in parallel, instead of in series, with a resistor, RE. So, the good news is, same RE. So if you want to find this RE, same thing, zero out all of the sources, find the equivalent resistance between the two terminals. IE is different. You have to find it by connecting a wire or shorting out the output terminals and finding out what current would flow through that short. Okay? That's how you find the equivalent current source. And I would say that just as we encounter voltage sources more frequently than we encounter current sources, we typically are going to use Thevenin equivalents more than Norton equivalents, but you got to be able to do both. So, conveniently, there is a way to convert between the two representations. So, the equivalent resistance is the same, like I said, but it also provides a bridge between Thevenin and Norton equivalents. So the bridge is that the Thevenin equivalent voltage source voltage is equal to RE, the equivalent resistance, times IE, the Norton equivalent current source. So if you had the Norton equivalent source, IE, and you had the equivalent resistance, RE, you could find the Thevenin equivalent voltage source, VE. Or if you had the Thevenin equivalent, VE, and the equivalent resistance, RE, you could solve for IE, the Norton equivalent source. So if you've got one, you can convert to the other one by either multiplying or dividing by RE. So that's pretty convenient. I have previously, on an exam, given somebody the Thevenin equivalent and asked for the Norton, or vice versa. And if you know this little conversion, you don't have to go through the whole derivation, which is pretty nice. This is like, tuck that little piece of info away for exam time when you're studying. All right, so now we have arrived at our example. So I want to find a Thevenin and a Norton equivalent circuit for this circuit. it's pretty simple, right? 2 resistors and 1 source. Could have made it much more complicated, but we don't want to do that much work today in class, right? We're just having a chill Wednesday. But I am going to make you guys do this problem. So I will get us started. I will say, okay, for a Thevenin source, we know we're going to have a voltage source, VE, in series with some equivalent resistance, RE, right? That's what we said. So whenever we find a Thevenin equivalent, we always get this, but we just need to figure out what VE and RE are. And so I would recommend that we start, and I'm going to toss it over to you guys, to start by finding the equivalent resistance, RE. Okay? So go ahead and get started, and I'll walk around and kind of help you guys think through this. I know you guys are having a chill Wednesday morning, but now I'm making you guys do stuff. Feel free to ask questions. Highlighter colors, like it. So we didn't remove it. We're coming up with an equivalent circuit that should represent this circuit. And so this equivalent, Thevenin equivalent circuit always is of this form, where you have voltage source in series with one resistor. So we need to determine what that resistance value is, RE, and what this voltage is, VE.
In series, you just add them together, right?
It's not quite that simple. At least I don't think it is.
Nice dynamics sweatshirt. It's pretty sweet. Hmm?
One of my favorites.
Yeah, rolling on an inclined plane. I like it. So, does anybody want to start us out finding RE? What are the steps that we need to take? Yeah, we gotta set the source equal to 0, right? And it's a voltage source. So how do we set it equal to 0?
Oh, or short.
We replace it with a short, right? So what we're going to represent it as, so I'll just do a little sketch over here. If we get rid of this guy, essentially we're shorting it out, right? So if I was to redraw this circuit, here's still our R2. this is still our output. Notice that it really matters where the output is defined, right? So this is our output still. This is our R2. And we could just draw our R1 up here like before, but since we're shorting out the voltage source, this is actually what's left. Can I will entertain objections to that. It's because if this is replaced by a wire, all of this is one node. And it's not until we redraw it that it becomes obvious that these two resistors are then in parallel. Before we shorted out the source, these two resistors were in series. Now they're in parallel. I know, it's like, whoa, mind blown moment right now. I know. Shivers. Oh man, Stranger Things new season comes out soon. So excited. So excited. If you haven't watched it, you're wasting your time right now in this class. You should be watching it.
What is it called?
Stranger Things.
Stranger Things. It's on Netflix. Oh, it's so good. Okay. Anyways. Yeah. So we're left with R1, R2. Does anybody want any more clarification on why that is? Yes.
So they're in parallel because of where the output is, right?
Because of where the output is. That's right.
Okay.
Really, in this circuit, it's always going to end up that way. But yeah, I mean, you have what I always go back to is what's the definition of parallel? What's the definition of series? And it's all topological, meaning how are they connected? Not meaning how does it look in the diagram, which I think is really hard to get away from because we typically will draw things in parallel on the diagram. So it helps us, but it also hurts us when we start to assume things. But this one is tricky because it goes from in one version of the circuit we're considering, it goes from being in series to being in parallel in another version, which is kind of hard. But I think that if you go back to the definitions, it's not too bad. And so how do we combine these two resistances to come up with our RE?
Isn't it just R1 plus R2? Because they're in parallel, not series.
R1,
Gonna want the
So it's the other one, right?
R1, R2 over R1 plus R2.
Yeah. So this is the sort of shortcut formula, right? But 1 over R1 plus 1 over R2 is the formula for resistors in parallel. In series, they would have been added, but since they're in parallel, they are combined this way. Okay, that's not too bad. And then the other part, which is admittedly a little bit tougher, what do we do for our VE? How do we find VE? Remember, I explained that you had to determine what the output voltage is with nothing connected to this output.
You're starting with VS with nothing.
Yeah, so you just need to decide what V out is, right? And that's going to be our VS in the circuit. Now, conveniently, as was pointed out a moment ago, we have a voltage divider circuit. We could go through the full circuit analysis, KCL, KVL, Ohm's law, like we did last time, but in lecture 1.3, we did a voltage divider circuit analysis, and we found a formula for how to get the output voltage given an input voltage across series resistors. So we're going to just recall that formula instead of having to go through it again. And I would encourage you to see this as an example of how ubiquitous this circuit is. The circuit comes up all the time, or some version of it. There might be 3 series resistors, but once you get to that point, you can just apply a voltage divider and you don't have to do anything else. It's a pretty sweet shortcut, and in fact, to foreshadow into next semester, there's a way to do this where you analyze other types of dynamic systems, and you can find what we're going to call transfer functions from one input to an output using this kind of idea very quickly, so that you don't have to go through all of the algebra. So I recommend getting comfortable with this idea of using a voltage divider, recognizing a voltage divider, and then applying the formula instead of having to go through the derivation every time. So our formula says that V out is equal to, and then we know it's going to be a ratio of resistances times Vs, the input voltage, right? What is that ratio of resistances for this circuit?
R2 over R1 plus R2.
Exactly. And that's because R2 is the resistor across which we are taking the output voltage, right? It's conveniently exactly the same as the one that we did in the previous lecture. I wonder who could have saw that coming. But it's also, if we had switched R1 and R2 here, what would the formula be? If we were taking the output across R1, what would this formula be?
R1 over R1 plus R2.
Exactly. So you take the resistance of the resistor you're taking the output across, and you're putting it in the numerator. And then you sum them all up in the denominator, and that's the formula. Pretty easy. And what we're recognizing here is that VE is just equivalent to V out. And so we're done. We've got our Thevenin equivalent source. We defined RE. We defined VE. We're good. Now we just need to find the Norton equivalent. And we could go back to the definition and short out the output terminals and determine through a circuit analysis what the current would be through that short. Or, and I'm going to recommend it, we could use our nice conversion formula to go from a Thevenin equivalent source to a current, or to a Norton equivalent source. So the circuit is, for a Norton equivalent, is always going to be a current source in, is it series or parallel with a resistor? For the Norton, it's actually in parallel.
Sorry.
So Thevenin is in series and Norton is in parallel. So IE is our Norton and RE in parallel. So we know RE, it's the same RE that we got in the Thevenin equivalent circuit, but our IE is different. And we could go through the circuit analysis like I said, but let's just use that nice formula that converts from a Thevenin to a Norton, which you have to solve for IE. Just is VE over RE. And we don't really even have to plug anything in because we already defined what VE is and what RE is. But just for the heck of it, let's do it. Let's look and see VE and RE have R1 plus R2 both in the denominators, right?
Mm-hmm.
So let's just cancel that. Let's not even write it down. Then let's plug in R1, R2 for RE, and R2 is left for VE. So R2 over R1, R2. So we get another cancellation. VS, which is equal to VS divided by R1. So that's our equivalent current source is Vs divided by R1. Whew! Not too shabby, right? That was pretty easy. Well, it's kind of nice that it's a simple circuit, so you didn't really have to do any circuit analysis. But a lot of them are voltage dividers, or at least you could turn them into a voltage divider by combining some resistances. So, good times. Okay, any questions on that? So I think that you now have the material to do all the homework that you need. And it, I mean, the reading gave it to you anyways, but now we've discussed it in class as well. Cool. So now all we want to do is another lecture. 1.5. So